Okay, so well, unfortunately, it was up to last moment I was supposed to come, but well, for some reason I came off. But I will try to do my best and make a presentation. So thank you very much for inviting me, of course. And this is I will speak about the Satake duality. Satake duality is something which is quite well known since 50s, but well, somehow not very popular. So I'll try to explain what is that, of course, first, and then I'll try to explain that some kind of analog of Satake duality happens for the character variety, and for, well, one can generalize it to the context of Teichmüller theory. So, in some sense. So, we start with just Satake duality. And so, well, I also would like you to ask questions because, well, you know, all the main problem with speaking the computer is that you have no, you speak to the empty space. So this would be very nice if you keep asking me questions. So, well, now let's start with the Satake duality. So if you have G is a symbolic group, and you can consider two different spaces. So first space is out of that you can construct just one space is very simple. So this is the spatial functions on the group quotiented by continuation. And this is a very well-known algebra. And another object is the following. So you take, instead of the group G, you take the group over around polynomials. So I'll denote by Q of K, and the uppercase K, and so by K, I'll traditionally it's just run polynomials of run polynomials of T, some variable T, and O will be the Taylor polynomials. Aren't series, but it doesn't really matter. Taylor's series. And let's take the group now with, for example, matrices of cell n with entries from one series, and then portion from right and from left by G of O. Sometimes this object is called affine inverse mean. And you consider functions of that. And the claim is that these two function spaces are isomorphic. Actually, these two spaces are isomorphic not only in the vector space, but also in the algebras. And the algebra structure on the space of functions on conjugate classes is, well, just obvious, just with respect to usual multiplication. And here we have multiplication. And here you have on this space, of course, you have usual multiplication as well, but it's not what you are interested in. You're interested in this function with respect to convolution. It's actually the Hecke algebra. Of course, formally to define the convolution, it's not possible because, well, you have some non-compact spaces, so you need to get around that. Well, I'm not, for a moment, well, I decided not to speak about the algebra structure here today, but so, well, you can do it, just considering, for example, over finite fields, so for this reason I didn't write that's everything you will see here, or take a characteristic, but well, nevertheless, you can define the convolution on this space. And there is this, sorry, what I really forgot to mention, that, well, in order to make it isomorphic, you need to replace here, not in group, here take the group G, and here you need to take the group, which is Langlands duality. I recall that, well, if G is, so G burn, this is Langlands dual, Q of G. Well, you will see in a moment that it's a very natural choice. So I'll try to explain actually this point as well. So what is this space? Let's consider the example, which is G is SLN. So for G where is SLN and G is GLN. So what is the space of the space on the right? So the space of functions on A G over F G just as the space of space with the base of characters given by characters of irreducible representations of SLN. So they are denoted by chi lambda, and these are essentially, well, Schur polynomials. Now let's take the functions on what is, first of all, what is G bird of K over G bird of O from the right and from the left. This is actually a discrete set. Well, there is a how can view that? So here you have a matrix with one coefficient. Here you have a matrix with table coefficient. There is the so-called Smith normal form. So if you have a matrix, in this case you cannot diagonalize it by action from the left and from the right. And the matrix of the form, the matrix of the form z to the k1, etc. z to the kn, with the property that k1 is greater or equal than k2, etc. Kn, and the sum of ki equals 0 because it's SL and not GL. So this is this double set. So double set is enumerated just essentially by collection of integer sets. It's a finite set, discrete set. And you can recognize that this set is essentially the same as on the other hand, the same set is characters. Well, what I denoted here, lambda, so these Schur polynomials, but well, it's not Schur polynomials. It's not arbitrary Schur polynomial, but Schur polynomials corresponding to the representation of. Sorry, I also PJL, of course, it's essential here. That you have the representation not of SL but P of PJL, and the PJL are the representation of PJL are enumerated by exactly the same set. So lambda is the same thing as lambda. So therefore, this is also this same set. So this is enumerated of the basis, the sets, the points here. So points are in projection. With ERAPs of PJO. And therefore, well, the spatial function of this space is, well, at least the Hecke basis, which is enumerated by the same set as the spatial functions on the space on the other space, this space. Well, this is isomorphism. This gives an isomorphism obvious between vector spaces, but this is a not exactly if we want to establish an isomorphism in algebra. It's a little bit more complicated. I'm not going to speak about how you need to just change a little bit the basis using what's called polynomials, but this is a kind of another story. So therefore, we establish some isomorphism, which is just you have functions on a finite dimensional space. And and on the other hand, you have cells. Well, the composition well, it's not cells in this particular case, not cell because they are not logically trivial, but the composition cells of your space G of k, which is infinite dimensional space, and the orbits cells are orbits. So cells orbits of G of O times G of O, and the cells for each cell you associate the functions. So the cells you get functions on this finite dimensional space. So the basis of functions is enumerated by cells of some infinite dimensional. So this is a phenomenon which corresponds to the Satake duality. Once again, this is true for any symbolic group. Just in my example, this is a finite dimensional group. So I would like also to mention that this space can be viewed a little bit differently. And
may I just ask a question? What are the cells for? What are the cells? I don't understand the definition.
Cells are orbits. So you have G hat, well, maybe a bird with the birds. So you have this infinite dimensional manifold. So this is the space, the group, but with coefficient integers in Laurent series.
Yes.
And on this group acts the group with coefficient in Taylor series. It gives it x from the right and from the left. Yes? And you consider the orbits of this group.
I see.
So the analog.
They're not
So the analog.
No, they're just over their orbits.
They are orbits, but the analog are just blue cells. Why? Because if you have the group G, well, maybe I will write it. Since you have group G, and you take a quotient by the Borel group from the left and from the right. So this quotient is very famous statement that is isomorphic to the Wien group.
I see. Thank you.
So it's a discrete set, and this discrete set are just what are inverse images of in G of elements of W. There are just orbits of action of browser.
Thank you.
So here, if you wish, it's just an analog of this construction, but in the dimensional setting. So instead of G bird, this is just you replace G by its affine analog, G of K, and Borel you replace by G of O, which is, well, almost the same thing. Actually, it's more than well. Thank you very much for this question, because also I wanted to say that just space. So I want to say that there is another point of view on this space. Well, G of K, Washington by G of O from the left and from the right. Well, matter from the right. So it can be viewed as you take an affine by group. But if it were a Borel subgroup, also well, if it were a Borel subgroup, then it would be just your it's isomorphic to the Wien group, but in this case it would be the affine one. And since this is quotient by G of O and not Borel, then this is a quotient of the Wien group from the left and from the right by affine dimensional Wien group. So W hat, this is a affine Wien group. And W is just order one. Wien group of G. Of G. And I'll need this affine Wien group very much. So for this reason, I'll mention what is it. So W, there are two different ways to, well there is one way to view the affine Wien group. So you take the Wien group is actually extension of the five-dimensional Wien group by the root lattice. So if you have the Wien group acts on the group lattice, five-dimensional Wien group, finite Wien group acts on the root lattice, and you can take the semi-Dirac product, and this is W hat. But for me, it would be better to view this Wien group in a little bit different way for SLN. So for SLN, just because it will be my main example, of course, for SLN, the Wien group looks the following. So usual Wien group is this, well, it's just permutations. This is the group XM with permutations. And this can be presented as a collection of the following objects. So it's my favorite way to draw an element of the symmetric group. So you have n points on the left, n points on the right. You have a strip. You have n points on the left and on the right, and you connect points on the left with points on the right. So you have such kind of diagrams with up to command. Each particular picture that gives you not only the elements of the symmetric group, but also the composition of symmetric group in a product of simple transposition, and this is given by this picture. So W hat is just a space of the same objects, but now on the cylinder. So you replace your strip by cylinder. You have endpoints on the left, endpoints on the right, and if you connect them, but in this case, you have right to go around the cylinder. And also up to command. And this is absolutely obvious that if you have an affine group, then still you have a permutation because you have correspondence between points on the left and points on the right. And the kernel of this map is just a collection of paths which connect each point with its partner on the right. So the only thing which counts is how many times it turns around. So this is always a particular case that you have W hat, it's mapped to Sm, to 1, and the kernel is just Z to the M, because 1 is Z to the M, and this is well, well, simply speaking, what I did is it's not SL1 case, but GM1. To make SL1, you need to pose a condition that, well, maybe I'm not going to speak about the details, but the idea is that you consider such diagrams with additional condition that the average shift of every point is 0. So one every time well, for every point you can associate a number which is how much shifts to the right and to the left, and average should be 0. It's not very common, so in this case you will have Z to the n minus 1 as the term of the Z to the n. The sum of these integers must be 0. Okay, so this is just a point of view on the W hat, and there are needed data. Well, now my main aim is to somehow describe well, I should have told that at the very beginning that very big part of what I'm going to speak about is kind of conjectural. So there are plenty of, well, so far nothing conjectural, but what I'm going to speak about local systems on Riemann surfaces, it will be, well, plenty of things will be, but definitely not everything. So I'll so analog with generalization for flat connections, local systems or the same flat connections. So the main well, there is a duality which tells the following thing, that the functions, well, this is kind of established, that the functions on the space of flat connections on M, G, X, well, X of G sigma well, I will give you the definition. It's the same thing as functions. On A, G, A tropical G sigma. So where chi of G sigma is the space of G-local systems, and actually G have local systems, so flat connections on sigma, on the Riemann surface sigma, or two-dimensional surface sigma, and a G, topical G of sigma is also a discrete set. Namely, is just tropicalization of G local systems on sigma. So, well, once again, I write just for specialists, I write X and A because they are a little bit different spaces. One is X type and A type. So this is a space where you have for SL2, this is a space where you have Langlands coordinates. Here we have the space of sharing coordinates. Well, this is more or less, but there is a functions of this space is the same thing. So it's kind of already kind of very similar situation to what we had before. So you have a continuous space, which is enumerated by with the basis of functions enumerated by the point of the discrete space. So these are by basis corresponds to basis to basic vectors in chi of GC. And these are, well, the points of this space are called sometimes, well, these points of this space, this is the A, one can call it A of G sigma. One can call their higher combinations because for XL2, these are just ordinary combinations, integral combinations, of course, on your surface. So these are generalization. So the rest, I talk more or less, I will try to explain that this space is very similar to the space of cells, which I started with, and just try to speak about what are different points of view in the space of higher dimensions. So this is a higher combinations and there are different points of view on the same space. The first thing that it's just a tropical bond. So I just repeat GC. So you take a modular space and then take it on the tropical symmetry. Second point of view, which I'll try to I'll try to explain. These are what's called integral spectral curves. The third point of view is that these are doubly head coverings of sigma. And the fourth are really high combinations in the same place as colored graphs. on sigma. So I will start with the definition number 4, and gradually I will get up that explain that this is actually the same object than the definition number 1. But from the definition number 4, it will be clear that this is related to this cells in the space of local systems with the value j hat. So what I'm going to explain that really this, if you consider the combinations not as just tropical points, but some more sophisticated way, not sophisticated, actually more natural from my point of view, then you get naturally the cell decomposition of some two-dimensional vector space numerated by this set. So what are covalent graphs? So the definition number 4 is actually higher combination. Is a graph on sigma with edges enumerated by generators of W hat. Maybe, well, I should also have told that what is the definition W hat. Also, as the ordinary computation group, it means a presentation of by generators and relations, and the fact is that W hat is generated by the set S I, where I are simple roots, simple positive roots of the corresponding algebra, and with relations that Si Sj equals Sj Si if the Cartan matrix is 0, and Si Sj Si equals Sj Si Sj if the Cartan matrix is equal to -1. And of course, Si squared is equal to 1. So this is a presentation of the double hat by generations and relations, which is actually for SLN. You can easily see it from the picture I gave you before. So this is a presentation of this algebra, and W hat is, well, of course, simple roots of the affine group. Simple affine group. The algebra. So this means that you add one additional root to the finite dimensional algebra. For example, for SLN, you have a linear diagram which is just closed poly. So there are just simple roots for SLN. Well, higher combination. Now we have a graph on the surface which is enumerated. The edges are enumerated by the generator of W hat, and with vertices of 3 types. So the first type is the following. So if you have you allow the three valent vertices A, B, C, A. So 3 valent vertices. Oh, sorry. The first type is just vertices with 3 edges of the same color, colored by the same thing. The second type is that you may have just two edges intersecting, but with additional condition that you have AB, and you require that CAB is equal to 0. So it means that the corresponding generators of your while group commute. And the third condition that you may have 6 dependent vertex with alternating A, B, A, B, A, B, with CAB equals to -1. So if you have this kind of relation, then it's, well, you may see that every vertex, well, these two vertices correspond to two relations. This is a commutation relation, and this is a relation of, well, this type. So maybe, well, but of course, I just consider the graph, all this graph, and all that is up to equivalence, which I'll, well, this is the most complete, well, no, it's not very explicit as a equivalence, so this is a kind of thing which well, it's not so clear what one can define in equivalence. Now, I want to say that, first of all, why this, I call this higher elimination, because, well, usually you know what is the usual elimination, and I want to explain that this picture is actually generalizing the usual elimination. And the reason is the following, that if you have, or suppose that you have n equals 2, so you have SO2 as L2. The elimination, so elimination is a collection of curves, of closed curves, closed single curves. On sigma, which you will know very well. So you have a surface and its curves on it. So the idea, so, well, for example, generically, you decompose the surface into either cylinders or elimination decomposes either cylinders or pairs of pans, or maybe something more complicated. So the idea is that you can, if you have a cylinder, so for each elimination in the conventional sense of your, you can associate a bicolored elimination. So you can draw color curves. So every time you have a cylinder, to draw a curve of another color, and every time you have a pair of pans, to draw a theta graph, which is just actually retract of your surface. So you have something like that. So you can retract, of course, with a pair of pans, or even you have some piece of surface which is more complicated. So you can retract it to a graph, unless you have, and this is unless you have just closed surface, but in this case, elimination is just trivial. And so you can retract to a graph. So you have a green graph, and which you can make permanent, of course. On the other hand, if you have SLM, then your group W hat is just a group generated by two generators, S0 and S1, with a relation of the only relation S0 squared equals to S1 squared is equal to 1. So this is a kind of very simple case where you have no relation between S0 and S1. Well, kind of exceptional because the corresponding element of the Cartan matrix, you have C01 is equal to -2, and in this case you have no relation between the generators. Sorry. So this is I want to say that for every elimination in the old cells, you can associate the elimination in new cells. Now, you have elimination in so elimination. Yeah, I want to define the following object. So compatibility. So definition, which is just crucial to define the sets definition, that X be now belong to M G hat sigma. So this is my main object, which I will divide into cells, and this is also the local system, so representation, the affine local system, so representation of pi1 of my surface into the group G of K. So these are now affine connections. So the connections, but now the value in this is Laurent series group. So group with coefficients in Laurent series, or of course you can view it as a family of connections depending on parameters such that every mathematics element is just a random parameter. This is the space. And L is a higher combination. And one say that definition, we say that the X is compatible with L if we can choose a covariantly constant flag on each face of L such that for any edge the difference, you have an edge covered by the cover A, and if you have the flag F1 on one side and F2 on the other side, then we want that the distance between these two flags correspond to the generator A. Maybe I should comment a little bit what it means. If you have a pair of flags, for affine or affine link group, it doesn't matter. So you have two pair of flags. So if you take a pair of flags, so Fi are since I consider the problem locally, so I can think this is just flat belonging to the same space. So you have so flags are belonging to my group. In those cases, a fine group, but the dimension you have, which is well the same as G of K. So F belonging to G of K quotiented by the browser. Well, this for 5-dimensional is the same thing. So, and if you have a couple of flags, so if you have G, well, quotiented by paradox group from derived from Langlands, once again, maybe I shouldn't even put X because it's true for any group. So you have G quotiented by Borel from right and from left, that you know that it's W. But on the other hand, this is the same thing as G over B squared, quotiented by G from one side. And therefore, it's also equivalent to W. G over B is just pair of flags. So pairs of, we have a map, pair of flags, 1 and 2, which can be sent to the space of pairs. There is a canonical map from the space of pairs to W. For example, what means that, well, yeah, so pairs for any pair of pairs is really an element of the vector. And then what we have here, so we have two flags, and if they are separated by an edge, then we require that this pair defines your element of the vector. Well, maybe just down to this. For SLN, for example, this A means that you want to, A is just for SLN, this picture means that you have F1, F2, two flags, and the simple roots of SLN are numerated by integer from 1 to n, and it means that this picture means that if I is different, if 1 is different from I2 from F2 in the I subspace only. So you have just one subspace which is different, and the other one side. So they are minimal difference distance between the two. So we have now the picture the following. So for every well, in general, you have some graph which is colored by different for example, something like that. So we have A, B, B, C, C, and you have every face you have a flag, and every time you cross the border, you change the flag, but change the flag in a minimal way. So you change just this line, just one subspace. And we say that therefore, for example, if you have some very simple example, if you have so if L is a trivial elimination, then it's compatible. It is compatible with elimination, which with flat connections with X in M G hat sigma if X preserves a flat, or X has has the coordinate constant flag. So this is actually means that X is representation not only of the whole group G hat, but only in its correct part. And this is a this is a part which is, of course, this is a which is not separated from trivial connection. So if you have a function of this space, then it's the same as the trivial connection. So, well, now the cell corresponding to definition, well, the cell corresponding to lamination. L is just this set of all X compatible with L. Well, once again, maybe I should make cell into commas because, well, so far I have no proof that it's conjecture. Well, that is actually a cell. However, I strongly believe that is the case. At least it's well, yeah, with some maybe with some exceptions. So it gives a cell decomposition of this this infinite-dimensional space. Well, so the position you need to prove that for any X. Maybe I also mentioned the following thing that two graphs. So far I didn't mention what means equivalence. So L is equivalent to L prime. To L prime, and here, unfortunately, I have no better definitions. So if so far, if the cells isomorph, the corresponding cells, are the same. Well, this is not very unexplicit definition. Of course, we would like to have more explicit definition, namely, we want L and N prime to be, well, some moves which I love. For example, we certainly have moves, well, if you have L is for example, L is equivalent to L prime, is if L prime. So if maybe I should just mention the example of some rules that if L has a component, a contractible component, then it can be removed. Yeah, there are other rules, but definitely I have no. So far, I have no idea how to list all the rules of transformation of L to something equivalent. Well, so far I gave the definition of higher elimination as this colored graph. Maybe I should also mention another. The last thing which I want to say that this point, there are plenty of points of view of Hennenfent. There is one also the generalized elimination, and there is one which is similar to what you maybe would which is kind of well, high laminations that I wrote before. One of the points of view of high lamination, these are integral spectral curves. And this is in the spirit. So this is in the spirit. Of Piotr Murnański. So this is the idea is the following: that so now I will give another definition, which is a little bit well higher laminations. Lamination is sigma tilde is a submanifold of dimension 2 in T star to my surface sigma. So with two additional conditions. The first condition that if you have projection, so the projection P, natural projection to T star to sigma, so if you take this is this is I will speak about SLA, not for E8 for example. P star is just covering is an n-fold cover of sigma, and 2 that, well, if you take the form alpha, which is just a canonical form on this page, T star of sigma, this is a canonical form alpha, so you take the sum over P star of alpha. I will denote just the sum of alpha over the sheets of this projection, so it must be 0. So this is this object, and also up to Hamiltonian equivalence. Sorry, I just forgot to mention a very important thing, that this embedding is not any embedding, but it's Lagrangian. So it's Lagrangian submanifold in T star of sigma, which is covering and with this additional condition. And on Lagrangian submanifold, there is so two Lagrangian submanifolds are equivalent if there is a Hamiltonian flow which sends one Lagrangian submanifold to another, maybe time dependent. So this is a equivalent borrowed from syntactic geometry. And this is well, now I will try to explain that this definition of high laminations actually corresponds to the definition which I gave just before.
Sorry.
About this colored graph.
Excuse me. Sorry.
The idea is the following: that if you have this Lagrangian submanifold, sorry, the first, once again, I forgot the following condition, that alpha restricted. What's really very important, that you have this canonical form alpha and you restrict it to your sigma tilde, then you want that to belong to H1 of the sigma tilde with values in integers. So I want this form alpha to have integral periods.
Sorry, we are running out of time.
And actually, the Langlands submanifold of T star sigma with integral periods is more or less the same thing as just you have a covering, and so you provide this covering with some integral form. So this is a equivalent to say. Now, well, the remark how to construct. So for high elimination no sense, high elimination in new sense, to high elimination of old sense. So for example, if you have a map from sigma to well, I will generalize the P. This is a map from sigma tilde to sigma cross R to the circle, which denoted by R over Z.
Sorry, we are running out of time.
So the this map is given by the following formula. So if you have a point on your surface Z, then of course on the surface you can just project it, take P of Z, and then you can integrate, well, up to Z of your form alpha. You pick a base point, so the result depends on the base point, doesn't matter. So you have this map. Since alpha has integral period, so this is well defined as an integral, and you have just a map of some yeah, okay, I'll finish very soon. Well, I have, yeah, exactly.
Yeah, okay, it's fine.
So,
It's fine. Okay, he got the message. Okay, thank you.
So this is a map, and you can imagine that what the how you can see the picture. So you have your sort of sigma. And above each point, so this is a product, above each point you have a circle. And in the circle, there is there is this sigma tilde, which intersects each circle in endpoints. Then you move your point, move along the surface sigma. Then these points, and this is sigma tilde. These points move around. And moving from one point to another gives you a map from pi1 of the surface minus perhaps some points, to the group W hat, because it's just gives you literally the diagram of W, which I drew before. So we have this map, and this I call the W hat bundle, which called before. So you have this map, and of course there are some points where your fibers are intersecting each other, and each point where it's intersecting each other, so correspond to the generator of your W. So therefore, the image here will be some the points that are intersect. They correspond to some generators of your W hat. So you get from self-intersections. So the graph, which I started with, is self-intersections graph correspond to image of the self-intersections. Of the image of C. So from well, this point of view, from sigma tilde with form, you get the graph. On the other hand, sigma tilde with form, so sigma surface with form, just by standard Hegelianization procedure, corresponds to flat connection. So this is a more or less, well, what I wanted to finish, but well, it's rather more or less automatic, but that its new sense of higher lamination correspond to the standard definition of lamination, that higher lamination is tropical level of flat connection. So, well, therefore, well, the moral of the story that one can, for groups higher than SLN, you can view what's the lamination, view geometrically, not only the tropical limit. There are plenty of ways to view that, and the most the idea I want to communicate now that you should involve the affine object, but particularly affine value group in the picture, and then you become more clear than this just fine dimensional groups. Thank you very much for your attention.